recording? Okay, let's get started. So for those of you that aren't in concrete design, you might notice on the camera, I'm on campus right now. With the weather last night, we had some power outages in my neighborhood. I took a picture a few houses down from where I live, and one of the transformers there, you can see, or the fuses was arcing and looked like it was going to catch the top of the pole there on fire. So suffice it to say, my neighborhood was out, so I came to campus to stream. I'm still working on grading the homework 7.2. I went ahead and posted the solution. It seems that some of you struggled with the deflection formulas, so I think what I might do is one of two things. I either am going to post a video going through those deflection formulas in a little bit more detail, or we might skip shear and just talk about that at the end, because shear, as you're going to see, is, and as we've seen so far, shear just isn't a big deal for steel beams. What I'm most interested in is the topics that I do cover, I want to cover well. And so if there's a struggle there, I think maybe we ought to just devote a day to that, just to make sure that we're all clear on how those analysis aids work. And it's probably not a bad idea to cover that anyways. But I'll let you know as we progress throughout this topic. At the very least, I do want to get discrete beams taken care of. So that's sort of my primary focus today. So we're going to get right into it. We're going to talk about discretely braced beams a bit, and how discretely braced beams fail, which is this discussion of lateral torsional buckling. Now, I do want to warn you, you are going to see some calculus. That's a typo. It's supposed to say wheel. We'll see. We will see some calculus. We will see some differential equations in the next few slides. I want to be crystal clear. I'm not going to make you do any of this on any homework or on the exams. I just want to provide a bit of background. And I really only have 2 points that I want to make with the calculus. But for now, I want to consider these two derivatives over here on the screen. Now, what I have here is the derivative of 5 times a function, and I have the derivative of x cubed times a function. Whenever, let's take the derivative on the left. So the derivative of 5 times the sine of x is, you factor the 5 out, the derivative of the sine is the cosine, so it's 5 times the cosine. The reason that we can factor that 5 out is because it's a constant, okay? Because it's a constant, calculus allows us to just pull that thing out and treat it like a constant. We can't do that, though, on what's going on the right. Now, if you remember, now again, you all can do this derivative. I'm not really concerned about that. What the point I want to make right now is that when you have a coefficient that's a variable, it becomes trickier. You can't just factor out the x cubed. You have to use, remember the product rule, the first times the derivative of the second plus second times the derivative of the first, and so on and so forth. Whenever you're dealing with variable coefficients, we can't simply factor them out like we would a constant. It becomes a bit trickier. I just want you to keep that idea in the back of your head for what we're about to talk about. It'll become important here in a second, but I just want you to keep that thought in the back of your head. Okay. Now, up until now, we've been looking at beams that were continuously braced. So we're assuming that they have bracing continuously provided along the top flange. So let's go back to how we described this from a notation perspective. For continuous bracing, we said that the LB term was equal to 0. And for continuous bracing, we said our nominal moment capacity was essentially equal to MP. Now we need to look at discretely braced beams. So instead of there being braces everywhere, there's only braces at specific locations. So for discrete bracing scenarios, we're going to be dealing with LB being greater than 0. So I have here an image that I've shown you before. I have a simply supported beam, and I have bracing at what we're calling third points. So remember, I can't stress this enough, there is a big difference between how long the beam is and its unbraced length. So if I were to throw some numbers out here, the beam might be 30 foot long in this scenario, but the unbraced length is 10 feet, okay? So there's a big difference between L and LB. For discretely braced beams, we know that LB is greater than or equal to 0, or greater than 0, I should say. But we don't know what MN is. We don't know what its nominal moment capacity is. And the reason why is because what happens when a beam is discretely braced, quite frankly, is a bit interesting, a bit quirky, and a bit complicated. Whenever you have a W shape that's being bent, there's a stability issue to consider. I got a typo there. There's a stability issue to consider. Part of the beam's in compression and part of the beam's in tension, right? You take a beam and you bend it, you know, if you bend it in smiley face bending, the top's in compression, the bottom's in tension. Whenever something's in compression, it wants to buckle, okay? But what happens is you don't have the whole thing in compression to a column. Like when you have a column, the whole section is in compression, so the whole thing wants to buckle. That doesn't happen here. Part of the beam wants to buckle, and part of the beam doesn't want to buckle. And so the only way for the beam to sort of deal with this is the way I like to describe it is it sort of kicks out and twists, and it experiences this sort of sudden lateral shift and this rotation, okay? And because it's deflecting laterally and it's twisting under a torsion, remember, you know, torsion is what causes twisting, we have a name for this phenomenon. We call it lateral torsional buckling, or LTB. I know that because we're at a distance, I know that sometimes it can be kind of hard to visualize this. So the first thing I want to do, I actually want to pull up this video. I found a video on the web that I thought was a pretty good view of a lateral torsional buckle experience. I don't know who the user is. This is, I probably can't pronounce that, but I want to give credit to them to posting this, because this is a really good illustration of LTB. So what we have here is a beam that it looks like it's in 3-point bending. I'm not sure. There might be another actuator back here, but you can see it's supported here on the left, and you can see this piston that's applying load. And I've got the video playing. If you look over here on the right, you can see this is the force. So you can see as it's loaded, this graph over here up top, this is showing how much it's deflecting downwards. I mean, you take a beam, you put load on the top, it's going to bend downward. But this one over here on the right, or on the bottom, is showing how much it's deflecting side to side. And there's something that happens here in about the next 10 seconds or so. Whoop, right there. You can kind of see it. The beam just sort of gives up, and it kind of suddenly kicks out and twists. Let me go back a little bit. You can see it right here. You can see it, and whoo, there it goes. It kind of kicks out and twists. And then if you skip forward a little bit, you can see how like it's really kicked on over to the left in this case. And so the beam kicks out and it twists suddenly in a buckling mode that we call lateral torsional buckling. So that's a really good visualization of LTB. I really think this is a nice, concise video of the effect. I also found a let's see. I found, where is it? I found this image. This is from a bridge in Canada, and let me pause this so it doesn't autoplay at the next video. This is from a bridge in Canada in 2015, and you can see that the bridge has undergone buckling. Oh, you go away. The bridge has undergone buckling, and you can see the same thing happened. It sort of kicked out, and you can kind of see that the beam twisted. When buckling is wanting to occur, the braces can see a lot of force. I mean, you can see the braces, they've given out too. That can happen too under these scenarios. You can find that the brace gives out before the beam does, or it's a combination sometimes of the two. But yeah, this is what happens with LTB. When LTB happens, it's kind of sudden, and in the field it's kind of scary. So it's definitely something to look out for. Now, like I said, the beam kicks out and it twists. So when I say twisting, I'm talking about torsion. So in torsion, we kind of need to talk about torsion a bit. And I don't want this to be a full-blown differential equations lecture or a repeat of Engineering 216, but I kind of want to talk a little bit about how these beams behave, and I kind of just want to set the stage for the ultimate point I'm going to make later. So when you all took Engineering 216, most likely, and most undergraduate mechanics and materials courses, mechanics of deformable bodies, whatever you want to call it, whenever you look at torsion, go find your old notebooks, go find your old homeworks when you look at torsion. And I would bet money that every one of your torsion problems related to sections that were circular, like a pipe, a shaft, anything that's circular in nature. Now, there's a reason for that. When we're designing something to resist torsion, we want it to be circular for two reasons. Circular sections are very, very efficient and under torsion, but two, whenever you twist something, when it's circular, it doesn't do a particular thing called warping. Okay, what warping means is that once you twist it, the cross section stays flat after it twists. Okay, and so we call that pure torsion. Sometimes it's called Saint Venant torsion. But the way that we compute the angle of twist is just TL over GJ. That formula should be somewhat familiar from Engineering 216, from deformable bodies, mechanics, materials, whatever you want to call it. If you want to write it in differential equations land, you'd say that the torsion is GJ times the rate of twist. And then we write it that way if the torsion isn't constant. The problem is that we're not dealing with a circular cross-section here. We're dealing with a non-circular cross-section, and non-circular cross-sections warp. And so what does warping mean? What warping means is that when you twist it, the section actually doesn't stay flat. The flange is like, if you were to draw the I-beam, the I shape on a sheet of paper, once it twists, the flanges actually go in and out of the sheet of paper. It doesn't stay flat after it's twisted. And the way that we handle that from a differential equations perspective is we say that it's the pure torsion minus the effect of warping torsion. And I don't want to get, again, this isn't a differential equations class. I don't want this to be really, really confusing. But all I'll say is the reason why it's a third derivative is because it's related to the shear. The second derivative is moment. The third derivative is shear. So that's why you have a third derivative term in there. Now, to give you kind of an idea and to put things in perspective with LTB, when we were dealing with column buckling, we only had one differential equation to consider. We had basically just the bending. And what we did is we solved this equation up top. We had the second derivative of deflection plus this term alpha squared times y, and alpha squared was P over EI. And that gave us this term that you see over here in the box. We only had the one differential equation to consider. But with beam buckling, with LTB, we got a lot more going on. We have the beam deflecting under the vertical load. We have the beam deflecting under the lateral load. And we have the beam wanting to twist. And so there's a lot more going on. So suffice it to say, this ends up being a little bit more involved to solve this out. If you wanted more detailed derivation, I'd be more than happy to provide it. I usually go through this in like in-class steel design, but I figure we don't really have time, and I don't really want to, that's not really the point I want to make. I just want you to recognize that this is a little bit more involved than just solving out a straight differential equation. Now, what ends up happening is after you substitute, a couple of these equations into one another and doing some simplification, we get these gray equations that you see here. And so it's literally a fourth order differential equation. And there's a lot of junk going on here. When you solve it out, when it's all said and done, you get this term here on the bottom, this MCR. So this is the moment that is required to cause buckling, or this is the moment that causes buckling right here. Now note, it's written in terms of LB, not L, because remember there's a difference between the length of the beam and the unbraced length. Again, I'm more than happy to provide a detailed derivation to get from point A to point B. Unfortunately though, there is a problem with this, okay? So in order to get from here to here, in order to get from these differential equations to a solution, and again, the solution is what we're after. That is the moment that will cause that thing to buckle. And so as designers, we want to know that. We want to know how much moment's going to cause this thing to fail, because we don't want that to happen. But in order to get from point A to point B, there's a little bit of a problem with this derivation, okay? So let me sort of explain that. So here's our differential equation, okay? This is the equation that we have to solve. And so notice, instead of writing it in terms of derivatives, like here, if you look at this slide, the upper expression, I've got in terms of derivatives. So it's like the second derivative or the fourth derivative. And so I did a little bit of shorthand and just used the phi prime would be the first derivative, phi double prime would be the second derivative, phi to the fourth would be the fourth derivative. If we look at this derivation or this differential equation, there's a problem. Remember those derivatives I showed you at the very beginning of the lecture? Like we had the derivative of 5x squared, and then we had the derivative of x cubed times the sine of x squared. Well, the reason we were able to factor the 5 out is because we treated the 5 as a constant. Well, in order to solve that differential equation, you have to treat all those terms as constants, okay? And so let's look at those terms and see, is there a problem? Well, what about E? Well, E is 29,000 KSI for steel. It's a constant. That's fine. G is a similar material constant. That's a shear modulus. If E is the elastic modulus, G is the shear modulus. It's also a constant. We can factor that out, no problem. What about IY? Well, IY is the moment of inertia. No problem. Now, if you go to the manual, let me format that. Hold on, that's going to bug me. Now, if you go to the manual, if you go to table 1.1, you're going to find that the manual lists J and C value, CW values for W shape. So remember, you can look up the depth of the girder, you can look up the flange width, you can look up the ZX, the radius of gyration. If you look at the end of that table, let me pull up my, let me go back to here so that you all can maybe kind of see me in the corner. If you go to the manual, and yes, I brought my manual with me. If you go to table 1.1, right, and you look here, I don't know, this is going to be horrible, but if you look here, you have the x-axis, the y-axis, and you look here over at the very, very end, the J and the CW values for every one of our shapes are listed as well. So you can find that. You can look those up. Those are constants, and we can factor out those as well. But the problem is the bending moment. That's the problem. See, we can factor out all the terms, but in order to solve that, we have to treat moment as a constant, and that isn't the case. I mean, let me ask you, how many moment diagrams have we ever seen that looks like that? That's very, very uncommon. Moment is usually a variable. And unfortunately, what happens is the differential equation becomes so complicated that it becomes really impossible to solve unless you treat moment as a constant. So how do we rectify this? How do we come up with a solution that we as engineers can use that will take care of this, that will resolve this issue, the fact that we treated moment like a constant, but it's really a variable? Well, the way that we handle that is we compute what's called a moment gradient modifier. It's this term C sub B. So for those of you that were in concrete design, C sub B was, we weren't even talking about the same thing. We were talking about bar covers in there. C sub B is what we call the moment gradient modifier. And so it's a pretty straightforward formula. And one way of thinking about C sub B is it's kind of like a slope measurement, if you will, of the moment diagram. It's not it's not technically the slope, but it gives you an idea of how much the moment changes within a given unbraced segment. So let me go back here to this scenario. Okay, so the way that CB works, let's go back to this. So remember, there's a difference between L and LB. This particular beam has 3 unbraced segments. There's a segment on the left, a segment in the middle, and a segment on the right. Each of those segments has an LB value, but it also has a CB value. CB is the moment gradient within that segment, okay? Now, the way that you compute CB is as follows. You use this formula here. It's a pretty straightforward plug and chug formula. What you do is within each unbraced segment, you compute what are called the quarter point moments. So let's say the unbraced segment is, I don't know, 40 foot long. So you'd compute a moment at 10 foot, at 20 foot, and at 30 foot. Those are your quarter point moments. It doesn't really matter if you go left to right or right to left because they're treated the same way in the formulas. That makes it pretty easy. And then M max is the maximum moment completely within that segment. A couple of points to keep in mind: all the moments are taken as absolute values. So if it's possible you're going to have a segment that has positive moments and negative moments. In fact, we're going to see that in our example in class. So take all the moments as absolute values and use factored moments. So for instance, considering this beam, I have a beam, it's simply supported. I have bracing only at the ends. So for this case, L does equal LB because it's only braced at the ends. If I put a brace in the middle, then LB would be half of L, if that makes any sense. Here's the moment diagram. That should be pretty familiar. So you again break it up into quarter points, MA, MB, MC, and then M max is the maximum moment within the entire segment, which also happens to equal MB. Okay. Also, if you look at this, MA and MC just by symmetry are also equal to one another. So that's only if the bracing is at the ends. Okay. So if you look at your homework, I actually give you a problem very, very similar to this, and I ask you to compute CB based on a couple different scenarios. The way that I thought I would handle this today is I wanted to give you a problem that was a little bit more involved than you would like. This problem is actually way more complicated than the problem I'm giving you on the homework assignment. The idea is I want to go through the really tricky problem here in class. So we're going to determine the CB values for each of the unbraced segments of the beam shown below. That should be segments. Okay, now we have a distributed load here. It's 2 kips per foot. We're going to say that's factored. We'll say it includes the beam self-weight. I'm really not worried about that. This is really more of a structural analysis consideration. I just want you to be comfortable with the CB computation. I went ahead and provided you the support reactions, and I've actually already drawn the shear diagrams and the moment diagrams. Let's go through that. So let's start off with the shear diagram. Remember, this is a factored shear diagram. So let's go back. This is structural analysis, right? So what do? We have a reaction of 22.5 kips. We go up 22.5. Then we go down at a rate of 2 kips per foot for a distance of 30 feet. So 2 times 30 is 60. If I'm at 22.5 and I go down 60, that puts me down to negative 37.5. Jump up a sudden 67.5 up to 30, and then track back down to 0. I also determine the area under the shear diagram. So remember, this is at a rate of 2 kips per foot. So this distance is just that divided by 2, and this distance is just that divided by 2. And again, these two distances add up to 30. The area under this triangle, 1/2 of this times this. Area under this triangle, 1/2 of this times this, and same thing. So remember, what should the moment diagram look like? It should go a lot to a little to a lot to a little. That should be, hold on, should be something like that. That should be pretty familiar at this point. I'm going to delete that because, well, I guess I'm not because it's bugging me, or it's not. There we go. That's better. And then if we go to the next slide, I went ahead and included that moment diagram. So if you see here, note, the moment diagram trails upward, trails downward, trails back up. Now notice I've got these vertical lines showing these are where the braces are. So there's a brace here, brace here, brace here, and it might be a little difficult to see on your monitors, but I actually have the grid showing up at quarter points. So I'm going to need a moment here, a moment here, moment here, moment here, moment here, moment here, so on and so forth. And so we're going to use this example to determine the CB value for each of these different segments, okay? Now, in order to do that, we're going to need some equations for moments, so we're going to break back some structural analysis exercises. But before I do that, I want to see, does anybody have any questions in chat before we move on? All right. Okay, so let's just sort of get right into it. So I want to go back to structural analysis land. Let me sort of redraw the beam here, and I want to redraw it without those braces. So here's the beam, and sorry. So here's the beam, and I want to just draw it without the braces. Seven. Now, let me redo that a little bit. Now let's go back to structural analysis land, okay? Those braces are just points on the beam. They do not change the moment function. Remember, the moment function is only a function of the loads on the beam and the supports on the beam. And whether or not, whether the support's here or whatnot. How many moment functions do I need to fully define the moment diagram based on this loading? I'm going to ask chat that. I want to see if y'all remember. How many moment functions do I need to define this, define the moment diagram? Here, I'll even pull the moment diagram up here so that we can see that. Okay. All right. Now you said 3, but okay. Now let's be clear. We're going to need 3 different CB values. I grant you that. But my question is this. Isn't this all just the same function? Isn't that all just one big curve? Because remember, how does this work? Remember, how do we determine how many moment functions we need? We cut a section. And so if I cut a section like here and look to the left, I see a reaction and a distributed load. What about if I cut a section here and look to the left? I see a reaction and a distributed load. Reaction, distributed load, reaction, distributed load. How many sections do I need to cut to fully define this moment diagram? It's not 3. We'll need 3 CB values, but we don't need 3 functions. It's 2, exactly right. All we need is a section here and a section here. All right. Now, let's remember one of the tenets of structural analysis, okay? I'm lazy, okay? I want the simplest problem possible. So let's take section number 1. If I cut a section right here, what is easier, looking to the left or looking to the right? I'm asking you. Let me go here. I'll pull this up. So here's the section number 1. If I cut a section, what's easier, looking to the left or looking to the right? Looking to the left. There you go. Exactly right. So let's handle that. Let's do that. So all right. I'm cutting a section, looking to the left. That's our shear. That's our moment. What's this distance? I'm going to have chat tell me, what is that distance there? Bringing it back to structural analysis. There we go. Everybody's remembering this now. That's X. This is 2 kips per foot, right? So we collapse that into a point load. How much is that point load? There you go. This is 2x, and I'll help you out on this part. This from the support from right here, that is x over 2, right? And then we sum moments at the cut. All right, so what do we got? We've got 22.5 times x. Then we have 2x times x over 2. We have m over here, right? We don't consider the v because the v goes directly through the section cut, and we list everything according to their correct direction. So 22.5x equals m plus x squared. So therefore, and because I've been kind of loose on the units, what I'll say is our moments and foot kips are 22.5x in feet minus x squared in feet. Would everybody agree with that? I want to take a second and see if anybody has any questions on that. Here, I'll pull it back up here. That way y'all can copy it down. All right, it looks like everybody's good. So let's let me. It's supposed to be an eraser. All right. Actually, let me do something real quick. Give me 1 second. So we have this equation here. Let's go ahead and compute the CB value. So let's do CB for leftmost unbraced segment. All right. So what do I mean? All right. I'm talking about, let me close this. I'm talking about this segment here on the left. So let me screen capture this to make sure that we're all clear on what we're talking about. So I'm talking about this segment here, and let's also be clear on what the moment diagram looks like for that unbraced segment. Looks like this. I'm just looking at this segment. Okay. Now let's be clear. What is LB for this leftmost segment? I want chat to tell me what's LB. I promise it's not a trick question. I just want to know what's the unbraced length for that segment, the distance between the braces. There we go. there you go. It's 15 feet. Is everybody clear on that? Because it seemed like there was a delay in the chat. I mean, if y'all have questions, please. I mean, don't hesitate. Okay. When I say that, I'm talking about just, again, the LB is just the distance between the braces. How far apart we are between these. Okay. Those are sort of like, they're sort of like these, like, you know, you've got those braces framing in right here. We're talking about the distance between those, okay? That's what the unbraced length is, okay? So again, don't hesitate if you got a question. I want to make sure that we're clear on this. All right, so in order to compute CB, what I need are what are called quarter point moments. So if LB is 15 feet, LB over 4 is 15 foot over 4, and 15 divided by 4 is 3.75. And the reason I'm saying that is because what I want is so here's a brace and here's a brace. So what I want is this moment, and this moment. Okay, now we were fortunate enough, we were given the MC value because that came from the moment diagram, but I want to make sure everybody's clear on where you can get that. Now remember, our equation is 22.5x minus x squared. So that's the expression we're going to use. So what we're going to get is we're going to say MA is M at x equals 3.75 feet. MB is M at x equals 7.5 feet. And MC is M at x equals 11.25 feet. So all I'm doing is I'm saying, you know, MA is M at x is 1/4 LB. MB is M at x equals 2/4 LB. And MC is M at x equals 3/4 of LB. So I'm just splitting it up into quarters. And so again, LB over 4 is 3.75, 7.5, and 11.25. So that's really all I'm doing here. So this first one, so we'll do the first one is 22.5 times 3.75 minus 3.75 squared. So somebody help me out with that first one. $70.31. That's what I got. All right. And so that ends up being in foot kips. MB, so this is 22.5 times 7.5 minus 7.5 squared. And so what do we get for MB? Somebody else besides Mr. Clark, or sorry, Mr. Schwartz. 1112.5, yep. And the last one, 22.5 times 11.25 minus 11.25 squared. There you go. So 126.56. Now, what happened is this just happened to equal M max. So we also need the maximum moment in that segment, but if we look at the moment diagram, that also happens to be MC, which is 126.56. If you go back to the shear diagram, remember, here's the shear diagram, and the shear diagram, the shear equals 0 at 11.25 feet, and that's where M max was. So it was just sort of happenstance that M max and MC are at the same spot. Once you've got this, okay, once you got this, the CB formula becomes pretty simple, and it's 2.5, sorry, M max plus 3MA plus 4MB plus 3, what am I doing here? 3MC, all under 12.5 M max. So 2.5 times 126.56 plus 3 times 70.31 plus 4 times 112.5 plus 3 times 126.56, all under 12.5 times 126.56. So somebody in chat, tell me what's CB for this segment going to be. We'll say like 2 decimal places. Anybody got an answer for me in chat? There we go. Yeah, 1.17. Good. That's good. Okay, so that's one of our answers. All right. Now, I'm actually going to skip the middle segment. I want to go to the rightmost segment next. In order to go to the rightmost segment, I need to look at section 2.2. Okay, so if we remember, here's the beam over here on the top right. We need to cut a section for this segment, and we need to cut a section for this segment. Okay, so what I'm going to do for section 2.2 is I'm going to cut a section and I'm going to look to the right because there's a lot less going on there. So if I cut a section and I look to the right, all I've got is I've got this. All right, and so I've got my shear, my moment. This is 2 kips per foot. I collapse that into 2x, distance x over 2. All right, and the reason I did that is because the moments are a whole lot easier. Because all I've got is I've got 2x times x over 2, and I've got m. So m plus x squared is 0. So my formula is a lot simpler. I got moment in foot kips is just minus x squared as long as that's in feet. So it's a lot easier. Okay, so I'm going to go through this one a little faster since we just did this and all the unbraced segments are the same, so now if I look at CB for the rightmost segment, again, we know that LB is 15 feet. So LB over 4 is 3.75 feet. So what I'm doing is I'm going to say MA is M at X equals 3.75 feet. MB is M at X equals 7.5 feet. And MC is M at X equals 11.25 feet. So all it is just minus 3.75 feet squared. Sorry, minus 7.5 squared minus 11.25 feet squared. And so since we're running short on time, I'm just going to give you these. This one is minus 14.06. This is minus 56.25. And this one is minus 126.56. Okay. And just so everybody sees where these values are coming from, we're talking about this segment right here. All right. We're talking about this segment. Okay. So we're talking about this value, and this value. Now, if you notice, if you look at the plot, we actually went right to left because this is minus 14.06. This is minus 56.5. This is minus 126.56. Okay. So if you notice, we went right to left, but that doesn't matter because you can go left to right or right to left. It doesn't matter. The formula will handle both. If you look at the way you handle MA and MC, you do the same thing to both of them. Now, M max is the largest moment in this entire segment, and the largest moment is actually the moment right here, which is minus 225. Now, you can get that from the moment diagram, or you can also plug in. You can use this formula and plug in X equals 15 and get minus 15 squared, and you'll get minus 225. So either way you want to do it is fine. And so therefore, you just do it again. CB is 2.5 M max plus 3MA plus 4MB plus 3MC, all under 12.5 M max. Now, the big thing to keep in mind is that when you plug into your CB equation, you take all of the moments as positive, regardless if they're negative or positive. You always use positive numbers. So this is 2.5 times 225 plus 3 times 14.06 plus 4 times 56.25 plus 3 times 126.56, all under 12.5 times 225. Now, when you chug this out, you're going to get the following. Give me 1 second. I'm getting 2 0.33. All right. I'm going to leave the chat open for a sec to see if anybody has any questions. We don't have time to do the central segment, but I want to show you. Well, I'll tell you what. I think we'll do. We'll do the central segment on Wednesday because what we'll do Wednesday is we'll finish that out, and then we'll look at how CB is used for capacity on Wednesday. But before I leave, I want to see if there's any questions in the chat on any of this. I'm going to give everybody a minute to make sure that everybody's comfortable with this, because I want to show you what you're going to do on the homework. I'll give everybody a minute. I know we're running out of time, but I want to give everybody a sec to ask questions if they have them. All right, let me show you your homework assignment real quick, because your homework assignment won't be influenced by that central segment. It won't matter. If you can do what we did just now, you can do the central, or you can do the homework. I want you to determine the moment gradient modifiers for this beam. So this beam is way simpler than the one we just did. The moment gradient modifiers for the beam shown for two different scenarios. So for one, if bracing is only provided at the supports, and other is if the bracing is provided at the supports and at midspan. So right off the bat, I notice I have a typo here. That's supposed to be 10 feet, not 20. This is what happens when you rush. But really what I'm after is I want you to look at the beam like this. If there's a brace here and a brace here. And second, I want to look at the beam if the brace is here, here, and here. Now, technically, the top beam only has one CB value, but this one has two. But because the beam metric for the second case, I'll go ahead and tell you the CB value for the left and the right are the exact same. Now you can use statics or table 323 to assist in computing the M values. I'd recommend you just use statics, what we did today, to do the M values. And I'll go ahead and also tell you something else. You can actually use table 3.1 to verify your answer. I haven't shown you table 3.1 yet, but if you find table 3-1 in the manuals, it's right before the ZX tables, you can use that to verify your answer, because it actually, I'll go ahead and tell you, the answer is actually listed in table 3-1. But I want you to derive the answer in table 3-1. That's sort of the whole point. I want you to understand what's listed in table 3-1. We haven't talked about table 3-1 yet. This is a perfect time to introduce you to it. Any other quick questions? Again, table 3-1 is right before the ZX tables, and table 3-23 is the shear moment deflection chart that we've used before. And I think what I am going to do is the lecture before the exam review. I think we're going to have just a lecture devoted to those design aids, those shear moment deflection aids, just to make sure everybody's comfortable with them, because I don't want that to be a sticking point on the exam. I want the exam to be on, you know, columns and beams and whatnot. Any other questions before we call it? All right, well, this is Dr. Mike from Marshall's campus for today, signing out. Everybody stay dry and stay safe, and I will see you all on Wednesday. That's all I've got.